Hi. So today I'm going to be solving problem C of the same contest I did last time. So this is Codeforces Round 841 Div 2. Um, I figured how to hide and show the zoom like toolbar, which is on Mac at least if you basically press everything key you can think of. So it's Control Option Command H to hide and control. You guys can't see what I'm doing, but it's hiding the status bar and showing the status bar for me, which is nice. So yeah, I guess now I just want to ensure that I'm sharing the problem screen and I want to hide it. Yep, and I've set an alarm for 45 minutes, so let's get started. Even subarrays, you're given an integer array A1 to AN and each AI is less than equal to N. That's nice. Find the number of subarrays of A whose XOR has an even number of divisors. Okay, number of subarrays. Okay, so that means like continuous sets of numbers such that AIs or AI plus 1 and so on, AJ has an even number of divisors. Yeah, okay. 2, 3, 5, 6 have an even number of divisors, while 1 and 4 have an odd number of divisors. Consider that 0 has an odd number of divisors in this task. XOR is the bitwise XOR operation. Print just print the number of subarrays. I mean, one thing is clear, like all squares have an odd number of divisors. And non-squares have an even number of divisors, right? Because yeah, that makes sense. Okay, so essentially you need to figure out if it's not a square. XOR is bitwise XOR. Yeah, okay. Let's look at sum of n overall test cases does not exceed 2 into 10 to the 5. Okay. Let's see. What is interesting is that it's not like a permutation, but you're just guaranteed that all the numbers are less than n. So let's look at, okay, before looking at test cases, do you want to think about something? I feel like XOR is an operation where like cumulative sum sort of thing is really useful, right? Because okay, now I do this whole sequence. Wait. Huh, I thought I just learned the shortcut. Okay, press escape for it to start. New share. Okay. Yeah, so XOR is one operation where like if this whole part is A and this part is B and this part is C, then like XOR of all the elements in C is equal to XOR of all the elements in A. XOR of all the elements in B, right? Because XOR is like its own inverse. So if you like do cumulative XOR, you can find XORs of any subarray. So you have that. Um, and you definitely can't do n square here, so you cannot. The easy way to do it would be the n square way, right? Literally find all the XORs and add them up, but you can't do that. If okay, let's try the examples. 3, 1, 2. 3 is 1, 1, 1, 0. So if I take just this 1, 1 not a square, this or this 1, 0 not a square, this or this or this, becomes 0, that's a square, that's have to be 1. So starting here, just this, yes, this or this. No, just 2. Hmm. Says the answer is 4. Ah, I see. I less than equal to j. Oh, sorry. I need to add up non-squares. So 3, yeah, that counts. 3 plus 1 counts. 3, 1, 2, that's a 0, that doesn't count. 1 counts. 1 and 2 counts. Wait. 1 doesn't. Array. Okay, huh. 3 counts. 3 and 1 counts because that gives me 2. 3 and 1 and 2 counts. Doesn't count, that gives me 0. Then 1 counts. No, sorry, 1 doesn't count. 1 and 2 counts. Because that gives me 3. And just 2 counts. Okay. Non-squares. Mm. See, if I saw any one of them, that doesn't count because if I saw any 2 of them, I get 0, that doesn't count. 3 of them, I get 4 again, that doesn't. So this should be 2, okay, 0. This is test case 1, test case 3, test case 2, 4, 2, 1, 5, 3. there a pattern I see? Like if I XOR, 4 is square, s square, no square. Oh, that's I don't think it will be like that. Or is it not like any properties, but like something basic? Like you sort of keep track of. Hmm. Seems like can we use the fact that you have only numbers up to n? Okay, yeah. You have numbers only up to n. The largest possible like square you could make, like, and I have no clue if you can make such a thing, is n square, right? So the potential squares are numbers 1 to n square, like all of those squares. Um, can you look at each of those squares and ask which XORs would give you those, which subarrays could potentially give you those squares? Um, but 1 to n square by definition has n different squares. Mm, are we already doing an O of n computation? Okay, suppose I had a square and I wanted to ask, and I had the cumulative XOR of everything. Then I could ask which XORs give me those squares. I feel like I'm not thinking hard enough. Okay. That direction doesn't seem to work. Um, oh, hmm. I'm drinking this like this will give me the solution. What other ideas? Yeah. Problem is not even some, it's some Zor nonsense. It's not like, is there any characterization for Zor? As in, like, how the Zor of a square might look. I mean, sorry, how the binary representation of a square would look. One, 4, 9, 16, 25, 16 plus 4. Is this even right? Yeah. No. 16 plus 4, 20. Sorry. 0, 1, 0, 1. Sorry. 16 plus 8, 24. Plus 1. 5, 36. I see no reason why a square should look special in binary, but just in case it does, 36. 32 plus 4. So, okay, let's divide the ideas into two sets. I feel like something that uses property of XOR and so on, and something that uses some basic binary search, cumulative sum type thing. So something that doesn't specifically use like a property of XOR. Okay, what are they asking exactly? They're saying find the number of subarrays whose XOR has an even number of divisors. That's the same as asking find the number of subarrays whose XOR is a square, right? Because you can just subtract n square this from n square and you get it. So, for instance, is it easier to think that way for the above thing? How many square XORs do we have? So size 1, 1 and 2. Size 2, not this, not this, this, right? This is 4. And this is 1106. No. Size 3. 1117. No. 1. Okay, this is 0. Middle one is 1. First one is 1110. No. And then this, right? This is 1 in the end, 0, 0, 1, 1 here, 0, 1, 0, 1 here, 7. No. So 0 plus arrays of size 4. 0, 0, 0, 1, 1, 0, 0, 1, 0. No, this 1, 1, 1. That's 1, 0, 0, 1. That's 0, 0, 0, 1, 0, 3. Versus how many total subarrays are there? 5. I counted something like awfully wrong. Oh, sorry. 3. And the number of guys that are there are so you can pick I anywhere. So you have 5 ways of picking I. Then you can pick J after I. Shoot, I don't know how to count number of subarrays. Wait, number of subarrays starting here is 5. Starting here is 4, 3, 2, 1. So 5 plus 4 plus 3 plus 2 plus 1. Right. That's the total number of subarrays. So that is 5 into 6 by 2. 5 3 is 15. Minus 3, 12. So I didn't count 1. So subarrays of size 1, 4, and 1. That was fine. Size 2. 1, 1, 0, 6 is not. This is not. This is. This 1, 0, 1, 0, 1, 1. This is not. Size 3. 0, 0, 0, 1, 0. 0, 0, 1. No. 0, 1, 0, 0, 0, 1, 1, 0, 1. No. 0, 0, 1, 1, 0, 1, 0, 1, 1. No. Arrays of size. Oh, subarray of size 5. I didn't count. Oh, okay, I probably did it correct. Okay, 1, 2, 3. That's 1. 1, 2, so that's 1, 0. Oh, okay, fine. I hadn't counted subarrays of size 5. So yeah, total minus this. Problem is to find some n log n, or n root n also won't, like, is too much. Number of guys that solve to squares. And I have like no ideas. Okay, I guess I have to see the editorial. As I had promised. Ideally, I want to spend some more time thinking about this. Yeah, I'm so reluctant to see that. Yeah, no, but that was the change I decided to make this time. Okay, nice. They have hints. What are the numbers with odd number of divisors? Those are squares. Ah, totally killed hint one. Hint two. How many squares can be in the range? This also I realized like root n squares can be there. Try to use prefix or literally I have all the parts. What am I not doing right? Hmm. If yeah, one issue is I thought okay, let me not pretend I got all of these hints. First thing I said there would be n square potential squares because each number could be n, and then n square. So n square is an upper bound, but I guess a better upper bound would be um, if you have the numbers n, right, you would represent them using log n bits, right? And the biggest number is all of those bits becoming one, right? So in the worst case, um, if n is a power of 2, a power of 2, um, mm, 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 then you have like, and the maximum number can be so n square, so 2n squares is the right answer, not n square, right? Because you represent a number n with, so for example 16 with log n plus 1 bits, and then if all of these guys are 1 you get 2 to the log n into 2, so n into 2 and up to 2n squares, right? Which was a good direction that I had. Um, okay, so say you have up to 2n squares. So 2n up to 2n. So number of squares can be root 2n, right? Root 2n. Root of 2n, say if you have a given square, how many subarrays of that square? Um, Say we have a root n times n solution. Let's attempt that, right? Um, hmm. If number of arrays that XOR up to a given number, that's all I'm finding. And how would I do that? Yeah, I'm not sure. I guess I feel like the reason maybe I didn't pursue this idea and actually think about a tighter bound on number of squares was because this is not clear to me how I can use okay, given a number, how can I find number of subarrays that XOR to that number? Even if I have cumulative XOR. Let's say in the cumulative XOR up till I found this number. What can I say now? Then this couldn't have been that number. Because if it was, oh, it could be. Oh no, say assume this is the first place where I found it, okay. Um, okay, yeah. This is assume this is like the first occurrence of this square number. Um, then if some subarray, some arbitrary subarray here was also equal to that square, that would only occur if this guy XOR to 0, right? Because this or this had to give me this. Right. So if some guy XORs to 0 and the rest XORs to that square, then only I'll get that square. Oh, that's true. That's true. So for any Oh, is that always? If this, no, that's not true. That's only if the square occurs in my cumulative sum. Otherwise, you could have, yeah, I'm stuck. If I look at the solution, I feel like I just get mentally exhausted so fast. And also, I'm on time constraints. Yeah, I'm looking at the solution. Wait, it's obvious how number of subarrays with a given XOR sum can be computed in O of n. How do you do that? Let's see. So LLN, input n, A of n, and M of 2 times n. I equal 0, okay. Int LL C and T count, I guess. 0. Car equals 0. I can't even understand this code. So there are two arrays. No, actually just one array M of size. I'm sharing. Okay, keeping the inner loop aside, I'm just seeing what the outer loop is doing. Cursor equals A of J, M of curve plus plus. So you are just doing cumulative XOR and I see. So at each value, at each index I of M, you hold so at each index L of M, you hold number of subarrays from beginning that XOR to L. So it could be this, it could be this, it could be this, all of these that XOR to L. Okay. Then you basically for each cumulative XOR, so for the number n, for each cumulative XOR, you go add n XOR that value. Why is that? M of n XOR that value. Because interesting. Yeah, if I'd known that, okay, fine. No excuses. Okay, some excuses. Yeah, if I'd known this is possible in orphan, I swear I would have got it. Yeah, I am stumped. I need to think about this Zor trick. So yeah, that's it for today. Crappy solving day, but I guess. Yeah, one thing I worry about is that I don't know that if I learn a problem, am I able to solve only a very small set of similar problems and like that sort of thing. But that's okay.